Good morning. Today's topic will be about the U.S. residential electrical system. In summary, we know that the electricity that goes to your home, or even like here in the wall outlets, is 120 volts, right? And also we know the frequency is 60 hertz. So the electricity, do you think for the wall outlet, is it AC or DC? What are your thoughts? DC or AC?
AC.
AC. Okay, and when I say 120 volts, is it the RMS or the max? What do you think? RMS, exactly. So we have 60 hertz. So if we need to talk about omega, 2 pi times f, 2 pi times 60, then it will be 377. That's what we see here. Now, I'm going to talk a little bit about the electrical system connection, like this. So we know the traditional power system or power connection, there is a power planet, and this power planet is being used to generate electricity, right? Then to generate electricity from the power planets, basically it can be based on steam turbine or combined cycle or single cycle, something that's related to mechanical engineering. And then mechanical engineers know better than me on this. Then after the electricity being produced from the turbine, then it will be connected, the turbine will be connected to the generator. So the generator will produce electricity by converting the mechanical energy into electrical energy. After that, we need to transmit the power to the load. Most likely, we used to have a large or big power planets. So these power planets will generate electricity on very large scale. Then it will supply several areas, different cities. Then, most likely the power being generated in 15 kilovolts, 10 kilovolts, 12, so something between this, like in the maximum, or I mean, I would say like between 10 to 15, 10 to 20 kilovolts. Then we need to transmit the power for longer distance, So we need to transmit the power for 100 miles, 200 miles, 50 miles, etc. Then if we need to transmit the power, as we mentioned earlier, there will be a losses. That losses comes from the line losses. So the power is actually being transmitted using the towers, like this tower. Since there will be losses, and we realized if we can make the voltage higher, the losses will be low, because the loss is I square times Z. So Z is constant because it's the tower itself, or the towers, or the power lines. Then I, if we figure out to reduce I, then we can get lower losses. We know S equal V times I conjugates. For the same amount of S, increase V, what will happen to I? Decrease. So if you increase the voltage, the current will be decreased. This yields to be lower losses. Therefore, the best thing to get a lower losses is to make high voltages. That's why we have high voltages nowadays. Then, if we make the high voltages, most likely the range can be up to 132 kilovolts. It can be 230, 400 kilovolts, 500 kilovolts, different ranges. These are very large values. And it's actually depending on what's the distance. So if you are transmitting the power for very long distance, then you need to have, higher voltages. If for fewer, it will be lower voltages. So, for example, I would say like if you transmit the power for 50 miles, maybe, or transmit the power for 500 miles, you will see different voltages. So this, there are a lot of calculations about this, but I would say like as, I would say that's the longer distances that we need to make the step voltages higher. Then, how can we step up the voltages from medium voltage to be high voltage? Medium voltage, like for example 15 kilovolts, to high voltage 132 kilovolts, by using a device called transformer. And since we will step up, we will go from 15 to 132, This is step up. That's why it's called step up transformer. And again, because it's transmitted from medium to high voltages. Then there will be towers. These towers, as we see if you drive in the interstates, then you will see sometimes some of these big towers. These big towers are actually 132. Sometimes you can see some other towers, extra large towers, which is 400 kilovolts, etc. So from the towers, it will be transmitting the power for 100 miles, as an example. Then it will go close to the city. For example, let's assume that we will have a power from Lagrange. Then it will go to Auburn. So you will see like these big towers. Then when we come close to Auburn, you will see an electrical substation that will make the power or convert the voltages from high to medium again. So what's the point why we're making it high to medium? You can imagine the electricity as a water pipeline. So if there is a large water pipeline goes to the city, this large will not go direct to your home. It will go from a very large radius, then it will be narrower, right? It will not go instantaneous from 132 kilovolts to be 120 volts. This is very hard and this is dangerous. So we will make it narrower. Again, imagine like a water pipeline that goes for the city, then for a neighborhood it will be narrower, then to at that street narrower, then to your home it will be very narrow. That's how you can imagine. It will be step down, will be done in steps. It will not be done at once. It's not like step up. Step up it will be at once, and we have from medium voltage to high voltage. But here we will have from the high voltages to medium voltages. So most likely the high voltages, again, it can be 132 kilovolts as an example. Then it will be converted to be 33 kilovolts. It's still not 120 volts. It's 33 kilovolts. We sell in kilovolts. Kilo means 10 power 3, as you know. Then at stage number 2, it will be called transmission substation. Then from step number 2, again, we have this system that we need to connect this after step number 2. It will go to inside the city or inside major cities. For example, it can go to Auburn, Opelika area, then you will have a large substation, then it will be converted also to a few lines that will go to Auburn, Opelika, Auburn University, etc. So most likely step number 2, transmission substation, it will be very large substation, and the equipments are very large. Then when we go from step number 1, after step number 2, to go to inside the cities, it can be as small towers, or it can be as a large pole, utility pole. So as an example, if you travel here in Auburn, like near to in Chuck Jordan Parkway, sometimes you can see a large utility poles. Or even here in the intersection between Donahue and the Wire Road, you will see sometimes some large power poles. Then after that, you will see some cables goes to the ground. We don't see these poles because inside Auburn City, inside Auburn University, it is underground. And even inside Auburn City downtown area, all of these electricity are coming underground because we need to have a distance to have a safe area. So whenever there is a downtown area or inside the university, all of these are coming as underground cables. Then these large power poles, these most likely can be in medium voltages as 33 kilovolts as one stage, maybe other stage 11 kilovolts. So, and you will see in the bottom as low voltages, so it can be used to distribute the local areas. So when we reach to that, for example, Auburn University, we need to step it down more. So it's 33 kilovolts. We need to make it step down so we can use it. So therefore, there will be another substation called distribution substation. And this distribution substation basically will convert from medium voltages to low voltages. So the output of it will be around 7.2 kilovolts. It's still in kilovolts, 7.2. As an example, you can see several substations here in Auburn. So in Auburn University, there is one small electrical substation close to the stadium. Where's the stadium parking deck? Behind this, you will see a small electrical substation. This is distribution substation, and this is converting the output of it around 7.2 kilovolts. And you can see as well, maybe if you travel in Dean Roads and the intersection between Dean and Glen, very close to here, there is also electrical substation. If you travel in Sanford and Wire Road, the intersection also there is electrical substation. So there are several close to us. Then these substations, again, converting the voltages from medium voltage to be low voltages. And if go to the industrial park, over industrial park, you will see also some substations like this close to us. Then the electricity now it's 7.2 kilovolts. Then it will go to the load. So inside Auburn University, as I mentioned, there are underground cables. So what you see underground cables basically based on 7.2 kilovolts. Then go to, for example, Brown Hall, Student Center. So there is electrical room for each building. In that electrical room, you will see another device, which is a small transformer, that will be converting the voltages from 7.2 kilovolts to be 120, 240, or 480, depending on each building. So for like here, Brown Hall, in this building, there are 3 types of voltages. So 480 basically for the 3-phase, 240 for 2-phase, 120 for single-phase. Then it will go to the wall outlets. That's overall. For the residential area, you will see if you travel in outside of the downtown area, where you'll see some homes, not apartments, where just homes. You will see these kind of towers, power towers, and these power towers, very close to close to a neighborhood, you will see a small device attached with that tower, like cylindrical device. So this device is called transformer. This is another transformer. This is the last step that will convert the voltage from 7.2 kilovolts to be 120 or 240. Then it will go to your home. And basically, that transformer will be 3-phase. What do we mean by 3-phase? We will say this later, but there will be several phases. So phase will go to your home. Phase A, phase B will go to your neighbor home. Phase C will go to the other neighbor home. Then, with these devices, again, this will be attached to your home. So you will see the voltages as, or this will supply your home. While if you are living on compound or apartments, there will be some electrical room that will take care of this. But here, if you are living in homes, you can see these kind of small transformers. So that's overall about the electrical connection. Now we will focus more on how we connect this to your home. Okay? Which is this area, between 4 to 5, or actually we'll focus on 5. So how the electricity will be connected to your home? That's what we call it U.S. residential electrical system, which is how the electrical connection to your home. Okay, so you can imagine that the utility side, again, the utility side, which is number 4, and home side number 5. So we will try to model this like this. So the utility side, or actually there is another image is better. Yes, that's what it is. That's what they want. So this is the power lines. That's very close to your home. Then we have transformer for each phase. Let's focus on one of these phases. So our topic is not about 3 phases. Let's focus on one of them. So basically, as I mentioned, it's 7.2 kilovolts, and it needs to convert the voltage to 240, 120. This will go to your home, to supply your home. So you will see the power lines. There is a fuse before that. That fuse is used for protection, to protect the utility equipment if there's some damages, if there's some short circuit happening at home and there is a lot of hazards going on. And what will happen? The fuse will detect if there is a very high currents, and it will be melted, so it will be burned, then nothing will be on. The power will be off to protect the utility side. While to protect the customer side, we have a circuit breaker. So most likely the fuse to protect the utility, from any damages going on. Because let's assume there is something happening in one of the neighborhood. We don't want this to affect on the whole neighborhood or on the whole city. So that's why we have this kind of protection. Then that device, again, is called a transformer that will convert the voltage from 7.2 to 240 or 120. How we can model this transformer like this. This is the schematic diagram. So it will convert the voltages from 7.2 kilovolts to be 240 or 120. And you see that there are similar to inductance, right, in the transformer. And you will see two parallel lines. So what are these? Why we model the transformer like inductance? Because actually, if you look inside the transformer, you will see it's basically based on coils, which is number of turns around a certain core. And that number of turns is basically the equivalent circuit of it is inductance. So the equivalent circuit of the transformer is a combination of inductance and several things. That's why we have this inductor symbol, because just to let you know that the transformer has an equivalent inductance or inductance behavior. Then you will see two parallel lines. These two parallel lines indicate there is a core inside it. And that core is sometimes can be ferromagnet, it can be from magnetic, several type of materials. Then at the other side, you will see three lines. Okay, how can we make this connection? I can explain it here. So in the utility side, here is plus, minus, or we can say this is plus, minus, or in other words, live and in neutral. I would say like VA and something like that. Or I would say like, let's see, keep it as live and neutral. And the voltage is 7,200, or in other words, 7.2 kilovolts. Okay? Now, this is the utility side. And what's the other side? Which is, this is the transformer, which is again, the transformer is this in gray area, gray shape. That's what we see, this is the transformer. Then in your side, which is the customer side, or would say like your home side, whatever. So you will see there are three lines, not two. The input is two, three lines. Okay, we need to have positive, negative. Okay, what's the point of the third? Actually, we have two positive and one negative. Or in other words, this we call it phase A, this we will call it phase B, and the negative we will call it neutral. Neutral is for the returning currents, and we have two positives. What's the point of having two positive? Why we don't have just one positive and one negative? The reason is because in your home, you have two voltage systems. You have 120, you have 240. Okay, how can we use this based on it? We can say that if you make the positive at A, the negative at a neutral, we will get 120 volts. If you make between a neutral and B, this we will get 120 volts. So this we can call it as VAN. I would say as a magnitude without bar, VAN, and this is VBN. Okay, so we can get 120 volts from different conductors, A and B, or A and N, or B and N. While how can we get the 240? What do you think? We can get it using KVL by A and B, right? So we can make the positive at A, the negative at B. So we will say this is VAB. Then it will be 120 plus 120, 240. 240 volts. All of them are volts. Then now, yes, we can get two type of voltages based on three conductors. So we can get 120 from different sources, from A or B with the neutral, or 240 from A and B. Okay, does this make sense? Now let's focus more on what will happen in your home. So based on that, in the customer side, there are three conductors, two live and 1 neutral, right? Or 1 for returning, 2 live, 1 for returning, or live and neutral. So we have 3 conductors. 3 conductors, 2 live, A and B, and 1 in neutral. Okay? Now, when we look at the wall outlets, we have 3 slots, right? So the question is, the wall outlet, is it 120 or 240? It's 120. Okay, so we have 3 slots. So we can say the first slot's live, this is neutral. How about the third one? Is the ground. Okay, now the ground is not here in that circuit. So what does this mean? Where does the ground go? Yes, to the ground. Actually, the ground is not connected to the utility system. The ground is connected to your home. And basically, you will see, or there should be, a ground rod for each home or for each area. That's the ground system is connected to it. Okay, what's the point of that ground? For example, you can look at some devices, like your cell phone charger. There is only live and neutral. There is no ground. Okay, for example, laptop charger, there are 3, live, neutral, and ground. If you take off the ground, will the system work? Yes, it will still work. It will be working. So the ground is not necessarily to run the system. We don't need the ground to run the system. Live and neutral, this should be fine. This is a completed circuit. According to our circuit analysis, we need to have a closed path. So live to neutral, this is closed path. Then problem done. Okay, what's the point of using ground? For protection. How? If there is something wrong happening to the system, like some short circuit, something happening, if the system is grounded, then that currents that we have that would causes the problem will flow into the ground. So we have a tool or some protection tool will detect if there is a current flowing into the ground, then the circuit breaker will trip. So this means the normal situation, there shouldn't be or there must not be any current flowing to the ground. If there is any current flowing to the ground, then definitely there is electrical system problem in your home. Then the circuit breaker will trip to prevent fires. Okay? So basically it will indicate there is a leak, electricity leak, something like that. So there is a leak, there is a problem. So again, the ground is very important for the protection, saves from fire, saves from different hazards, but it's not essential to run the system. Then, again, the standard voltage levels that we have, 120, 240. So in this system, we're not going to talk about the ground because, again, to run the system A and B, live and neutral, so we have 2 lives, A and B, 1 in neutral, N. So to get 120, connect A and N, live and neutral, to another 120, B and N, live and neutral. If you negate 240, then you need to connect live and live, which is A and B, which is basically 120 plus 120. So you can say, in other words, VAB is actually VAN plus VBN, something like that. Okay? So we can get 120 plus 120, 240. This is how the electrical, again, system connection. Then the conductors or the electrical system here, as I said, it will go to your home. Now, what's the first electrical connection at your home? What do you think? What's the first electrical connection after the meter? There is a meter. After the meter. So you basically, after these 3 conductors, they will go to the meter. Then it will go to where? Circuit breaker panel. Right. So circuit breaker panel, I think you are familiar that, or you see this type of panel like this, or even like this panel. You can find it everywhere, even in the lab, if you're in the research lab or in any building. So you can see this type of circuit breakers in your home, and you can see it. So what I encourage you when you go back home, open that circuit breaker panel and try to understand what does each breaker mean. So why we have these type of circuit breaker, you would say, why should it be one? And that's it. Why we have multiple circuit breakers? Okay, the overall idea is related to if there's something wrong happening in one of the rooms in your home, this will not impact the others. Like what? Let's assume there was a short circuit in the wall plug. We don't want to disconnect the lights, disconnect the other rooms because of the problem that you have here. So we don't want you to stay in dark because of short circuit happening in the wall plugs. So basically, the lights circuit breaker will be different than the wall outlets circuit breakers. And also, the air condition will be also split. So if you need to do a maintenance on the air condition, just disconnect the circuit breaker of the air condition while keep the other system or the other electricity, keep it supplying your home without any problem, without any interruption. So basically, each circuit breaker has its own function. One of them you can see when you basically you will see like as a label here. You can read it when you go there to your home. Label here, or sometimes they can write it in the circuit breakers, close the circuit breakers. You will see one of the circuit breakers for air conditioning, one of them for refrigerator, one of them for example, kitchen lighting, one of them for bedroom lighting. So you can see several ways, several things. Then each one, again, has its own purpose. And of course, there should be one main circuit breaker. So main circuit breaker for the whole home. Okay? So again, each one has its own, then we have a main circuit breaker. Now, what's the circuit breaker do? What's the point of using circuit breaker? Or what's the function of circuit breaker? Okay, we can use it to disconnect the electricity, right? Manually disconnect. But is it working also automatically? What do you think, yes or no? Yes. How? If there's something wrong happening, it will trip. Okay. How? Based on what? How can we know, or how can the circuit breaker detect there is a problem? What do you think?
Fuse.
Like what?
A fuse.
A fuse, actually, I would say like about the fuse, it is detecting high currents and it will be melted, or it will be broken. So the fuse, actually, if it's been broken, you need to replace it. So while if there's something wrong happening to your home, you will go to the circuit breaker and turn it on. You will not replace any device, right? So I don't think it's a fuse. So what's the purpose of the circuit breaker? How the circuit breaker run? Any thoughts? Okay, let me just talk a little bit about Ohm's law. Ohm's law, we know I equal V bar over Z bar, right? Let's assume short circuit happens at your home. Short circuit happens means what? Let's assume there is a wall plug, here is live, here is a neutral, then short circuit happens. This means that the impedance will be what? 0, right? So let's substitute this here. So we have the voltage as 120 volts. Then the impedance is 0. Okay. Any number over 0 is what? Infinity. And in electrical engineering, we will not say infinity as the infinity in math. We will define the infinity as very large currents. Okay? Very large currents. That's how we define the infinity. This means there will be very large currents. If there is no protection device, what will happen? This very large current will flow into the wires. And the wires, there is ampere capacity for each wire, or there's a capacity for each wire, because the wire has an internal resistance. The losses of the wires, I squared times R. If the current is high, this will make the losses high, right? So if the current is infinity, the losses will go to infinity. In other words, it will go to very high value. Okay, what's the point? If the losses will go as what? Or as we know, the energy, it will be transferred from one form to the other form. The energy, when it goes to the losses, it will be transferred as heat. Okay? The losses goes as heat. So loss will be as heat. Heat will cause the wires to be melted, or the conductors melted. And of course, melted causes fire. High temperature will cause fire, right? Then there will be fires, as you heard, like there is electricity connection happening at one of the homes, and we heard like, okay, there was fire. There was a fire problem, right? Okay. Now we don't want this to happen. We need to prevent this. And short circuit happens frequently at your home. It can happen a lot. Even at my home, happens a lot. Maybe 2 times or 3 times a year. It depends on if you're working a lot in your system or in your home. But it can happen short circuit. So how can we prevent this? The main reason that we have a problem is very large current, right? So basically, we need to use a tool that detects high currents. So we need to have a tool that detects high current. If there's a high current, it will trip. And that tool is called circuit breaker. Or in other words, I can call it a CB as a shortcut. So here's the point of using circuit breaker. It's not only for the manual, yes, for the manual switch on and off, and also it will work automatically to protect you from any problems that you have. So it is circuit breaker detecting the high currents. If there's a high current going on, it will be turned off. That's one job of the circuit breakers. However, like there are several jobs about it, but I'm not going to go through it. I'm just talking here about the residential electrical system. That's the main target about circuit breaker in your home. That's the main reason. So it will detect there's a current. So if there's any short circuit happen, it will protect you. So if, for example, someone go to the wall plug and try to connect live and neutral together, try to make short circuits. This is dangerous, yes, of course. But do you think you will be electrocuted? If you have a good protection system, the circuit breaker will trip automatically without harming you. That's what's supposed to be. I'm not telling you try it and do the short circuit by yourself, but I'm telling you that's what's supposed to be. So the response for the circuit breaker should be within a few milliseconds. It should be fast. So to prevent from fires, to protect lives as well, if there's someone working on the electrical connection and there's short circuit happening, so we need to protect lives. So it should work within few milliseconds. It should trip. However, we have sometimes some problems for the circuit breakers. This might not trip. That's why sometimes we hear about some fires. So there's a problem that we don't like. We call it circuit breaker failure. Circuit breaker, again, basically it's a mechanical switch. It will be turned on and off. And sometimes it can stuck in the middle. It can happen. It's rare, but it can. So in these type of problems, if there is circuit breaker failure, okay, we are in danger. So what should we do? We need to have another backup protection in case of the circuit breaker failure. That backup protection based on the main circuit breaker. So we need to have another circuit breaker main for the whole home. So if there is the circuit breaker with this room is filled, then we have the main circuit breaker that will trip if there is any problems. Okay? Does this make sense? So again, the main circuit breaker, the purpose of it, again, the first thing, as a backup protection, or if you need to disconnect the electricity from the whole home, you can use it. So yes?
If the circuit breaker gets stuck in the middle, do you replace it?
Sometimes just try to move it by yourself. So it just stuck, then you can move it. So if it's happened frequently, then definitely you need to replace it. Then let's assume there's a short circuit happening at your home. Then suddenly the power is off for the whole home. Then basically you can recognize that there is a circuit breaker failure in your home. That happens to me once, actually. In I think last year, there was a short. I was making some light bulb, trying to fix the light bulb. Then there was a short circuit happened, so the power was off for the whole home. So I went to the breaker panel. I see the main circuit breaker was off, and the circuit breaker associated with that room was in the middle, was not moving a little while. So what I did, I removed the hazard, removed that light bulb, and reconnect the system, and try to move back and forth the circuit breaker that was not working well. It worked well after that. So it can happen sometimes. So we cannot guarantee 100%, but of course our target is to make the accuracy as high as possible. And there is also something that we call it circuit breaker coordinations. Like what? If there's a problem happens, something wrong, we don't want the main circuit breaker to trip first. We want that circuit breaker associated with this room trip first. If not, the other one will work. There's something we call it protection coordination. There should be a time slot coordination for that breaker to trip. So let's wait, for example, let's assume that the circuit breaker should respond within roughly number as 5 milliseconds. If not, at 7 milliseconds, the main circuit breaker needs to take an action. So we need to give him some time to take an action. If not, I will take an action, something like that. That's the overall idea about the circuit breakers. Now, again, we have the main circuit breaker, as I mentioned, and the main purpose, again, protection to connect the home. Then the main circuit breaker will be connected to bus bars. This bus bar will be connected to the local breakers. This is how the electrical bus bar will be. So we have the meter. Then after the meter, we will have the main circuit breaker. Then it will be connected to several areas. Then by looking at the breakers, you will see the main circuit breaker connect 3. Main circuit breaker connected 3 conductors. You will see some breakers connecting 2, some breakers like here 2, some breakers 1. What does this mean?
120 versus 240.
Exactly, 120 and 240. So here we can say 240, this is 240, this is 120, etc. This is 240, this is 120. So basically, whenever there are double pole switch, this means live and live, then this is, we will use the 2-pole switch, which is 240. If it's single, then this is 120. Again, when you go to your home, look at the panel, then you can say, okay, this is 120, this is 240. Okay, how can I know this is the main circuit breaker? It will be in 3-pole, 3 things. The main circuit breaker based on 3, while the others 2, 2, 2, or 1, depending on the voltage level. So that's, again, here, how's the panel. This is like 3, main circuit breaker. Then this is double, 2, which is 240. This is alone, 120, etc. And of course, you will see the description here. Sometimes, some panels, the main circuit breaker will be at the top. Some panels, the circuit breaker, as this one, can be between them, like this one. Now, in this picture, where is the main circuit breaker? Where is the one that has 3, right? This is the main circuit breaker. Now, can you recognize where is the 240?
One's with 2.
Exactly. This is 240. While the remaining are 120. And also, when you look at this at home, you will see, for example, this is a main circuit breaker like 100, or when you look at the 240, you will see, as an example, this associated circuit breaker with air conditioning. Maybe 240, this circuit breaker associated with water heater. So the 240 are basically for the element or the devices that are consuming a large amount of current. Okay, again, what's the point if using 2 voltage systems? Why we didn't use 120 and stop? Because sometimes some devices that consume a large amount of energy, 120 might not be enough, sufficient to supply this. Then to get a better performance, we need to have a higher power level, because we know the power V times I, right? So let's increase V, double V, then we can get a higher amount of power, right? So that's why, and as maybe the disadvantages of 60 hertz systems or the US systems over the Europe system where it's 50 hertz. 50 hertz, they don't have 120 or 240. They have 220 volts or 230 volts. It's a constant, it's a solid. There is no 2 voltage system. It's only 1 voltage system. You can supply at wall outlet, you can supply at everything. So that's advantage. Disadvantages, maybe more dangerous because 220, 240. While in the 60 hertz systems, the disadvantage to voltage systems, while the advantages is higher accuracy or higher efficiency, and the advantages also is safer when we are in 120 volts. Then, again, you will see, again, this one goes to your home, again, like air condition. This one has heater. Then you will see some circuit breakers associated with light bulbs, some circuit breakers associated with the wall plugs. Now, let's look also talk about the single or the 120 volt circuit breaker. This 120 volt circuit breaker can be defined into two categories, two parts. One part associated with the lights, one part associated with, for example, wall plugs. What's the point of using this? Most likely the lights will not consume a large amount of energy. So the lights circuit breaker will be detecting a large current. It can be, as an example, 10 amperes. While the plugs or the wall plugs, maybe you can connect some devices that are consuming a larger amount of energy. This will detect a higher currents. It can be, as an example, 15 amperes. So that's why sometimes the circuit breaker for each one can be different, even if the same, this 120, but this one has different settings. Each one has its own setting. Then, again here, when we deal with 120 volts, we have circuit breaker 15 amperes, we have 20 amperes. Here, like 15, 20, maybe in Europe there is 10 and 15, so whatever here. 15 amperes, this is, again, it can be used for lighting. Lights. 20 amperes, it can be for applicants, kitchen applicants, etc. And you will see a word called 14 AWG, 12 AWG. What does this mean? Remember when we said that if there's a losses or there's a large amount of currents, there will be a thermal, the wire will be melted, right? So this means the wire has a thermal capacity, right? After that temperature, it will be melted, it will be broken. And when we link the thermal to the currents, there will be ampere capacity, right? So we will call now the wire as has its own ampere capacity, and this ampere capacity depending on how much current flow. Then, in order for the wire to flow or for the current to flow without causing any problems, there is a certain limits for the current to flow. Then, how we can define this? You can imagine the water flowing with a pipeline. You can see like the larger radius, the more current that can flow, right? The narrower, the less current can flow, right? So we can say that based on the ampere capacity, there is a specific number of thickness for the wire, so the current will flow. So basically, we defined the thickness as AWG. We have 14 AWG. You can even write in Google what does AWG mean and AWG charts. We have 10 AWG as an example, etc. Different numbers. So the larger number AWG, the lower or the lower thickness, or which is the narrower. So the thickness will be higher with lower number AWG. In other words, the lower number of AWG can handle larger currents. So AWG 14 can handle 15 amperes. AWG 12 can handle 20 amperes. AWG 10 can handle 30 amperes, etc. Maybe AWG 16 can handle, I think, 10 amperes. So we have ampere capacity for each wire. Therefore, since this wire will be connected to the circuit breakers, therefore, whenever we're dealing with the light circuit breaker, we will use AWG 14. When we're dealing with the applicants, we'll use AWG 12. That's our standards. Okay, so we can avoid that. There will be no problem. Now, with 240 volt circuits, basically, since we are consuming a large amount of currents, the breaker will be based on 30 amperes or 50 amperes. So it can be AWG 10 or 8 or 6, whatever, depending on the need. So you can see your home, there is different thickness of wires based on the applicants. And the thickness that goes to the wall outlet different than the thickness that goes to your lights, different than the thickness that goes to the dryer or the washer, etc. Okay? Now here's an example of how we, the overall connection. So basically in that system, that example, you need to know how to convert, just the overall idea, this number to be a complex number. So if we have 5 kilovolts ampere, 80% lagging power factor, how can we convert this to complex number? Complex number, S angle theta. Now kilovolt ampere means S, since it's volt ampere. So it will be 5 kilovolt ampere times 10 power 3. Angle theta is actually cosine inverse. Cosine inverse of power factor, which is 0.8, and it's positive because it's lagging. This is, just the point that I want to say about how to use these numbers. So anyway, that's the overall idea about how the electrical system connection will be at your home. Basically, comes from the utility side, 7.2 kilovolts. There's a small transformer, then go to your home. That small transformer will convert it to be 120 to 140. There will be 3 conductors. Based on the connection, you will get 120 to 140. Then you'll have different circuit panels. The circuit panels you can detect how much, the circuit panel will tell you how much current can handle, or how much was the wire conductance, the wire specifications for it. Then next lecture, we will discuss the multi-phase or the 3-phase. The overall phase that you need to worry about, which is, we know there's 3-phase system, and we discuss the AC single phase. And the AC single phase is working perfect. What's the point of using 3-phase? Next lecture, we will talk about it. Thank you.